We have the linear differential equation y prime plus 2xy equals x cubed. We're going to solve it using an integrating factor. And that's a word association or mental association that would be useful. First order linear differential equation, integrating factor. We see here the equation is already in standard form because the coefficient of the y prime term is 1. We identify that p of x is equal to 2x. And so we have the integrating factor mu, which is e to the integral of p of x dx is equal to e to the integral of 2x dx. And so is e to the x squared. I'm generally not going to go through the steps I'm about to do, but I want you to see the formal approach before I go to kind of skipping some stuff here. But we're going to multiply both sides by e to the x squared, and we end up with e to the x squared y prime plus 2x e to the x squared y is equal to x cubed e to the x squared. Now the left-hand side can be considered to be the derivative with respect to x of e to the x squared times y. It would be a good idea for you to differentiate this using the product rule to convince yourself that that's indeed what we have. And it's always the case that the function that we get, that we call mu, is the thing that's going to be the factor next to y in that derivative of the product. Now we've only rewritten the left-hand side. The right-hand side stays the same. One pitfall to watch for is forgetting to multiply both sides by mu. We get so focused on the left, it can be really easy to forget to multiply on the right, and that'll just mess everything up. Now we're going to integrate both sides with respect to x. And the left-hand side, we just pop out e to the x squared y. On the right-hand side, there's an integration by parts. Without going too much into detail, if I identified dv was equal to e to the x squared dx, we would have a hard time anti-differentiating that. So we're going to throw in a factor of x. That way we have a substitution there. That leaves u to be x squared. And if you carry that through integration by parts, after a couple of rounds, you'll find that the equation becomes e to the x squared y is equal to 1/2 x squared e to the x squared minus 1/2 e to the x squared plus c. Solving for y gives us y is equal to 1/2 x squared minus 1/2, so the e to the x squared divides out of those terms, plus c e to the negative x squared. You're going to find I'm more likely to write a negative exponent than a fraction. Now that's the solution of the differential equation. And when we look at both the original differential equation and the solution, we see there are no restrictions on x. Nothing's undefined or anything. So the interval of solution is negative infinity to infinity. And I'll point out that if x were to go to infinity, this c e to the negative x squared would end up going to 0. And that makes c e to the negative x squared what we call a transient term. If you look back at the instructions, you'll see we were asked to identify that. And I'll further point out this y equals 1/2 x squared minus 1/2 is what we refer to as a steady state solution. It's the solution that endures, if you will, as x goes to infinity. Moving on. Now we have the equation quantity 1 plus x times dy dx minus xy is equal to x plus x squared. Because the coefficient function of dy dx is not 1, this is not in standard form, so that's our first step. Dividing both sides by 1 plus x, we get dy dx minus x over 1 plus x times y is equal to x, because you'll note that right-hand side factors, and then we can divide out the common factor of 1 plus x. P of x is then equal to negative x over x plus 1. That negative needs to come along with p. Forgetting that can cause all kinds of problems. And aside from that, it would be incorrect. Now using either long division or adding and subtracting 1 in the numerator, and then applying that negative, we'll find that we have 1 over x plus 1 minus 1 as p of x. Mu is then equal to e to the integral of p of x dx, which is equal to e to the integral of 1 over x plus 1 minus 1, that quantity times dx. That's going to give us that mu is equal to e to the natural log of technically absolute value of x plus 1 minus x. However, remember that a solution is only defined over one interval. And here we've divided by 1 plus x in an early step. That means that x has to either be greater than -1 or less than -1. We wouldn't consider both intervals simultaneously. Therefore, I'm going to go ahead and assume that x is greater than -1 because I have no information that tells me I should consider negative values for x. And for that reason, I'm going to drop the absolute value bars. And because of properties of exponents, that's going to give us x plus 1 times e to the negative x. We'd multiply both sides of the standard form equation by that integrating factor, but the left-hand side is going to have the form of a product rule derivative, if you will. So I'll just go straight to, it's the derivative with respect to x of x plus 1 times e to the negative x y. And on the right-hand side, don't forget we need to multiply that x times our integrating factor. So we have x plus x squared times e to the negative x. We're going to get out of this mess by integrating both sides with respect to x. On the left-hand side, we simply have our x plus 1 e to the negative x y. And on the right-hand side, we have an integration by parts. Ooh, I neglected to write a dx on the right-hand side. Some people would distribute this and then do multiple iterations of integration by parts. I don't recommend that at all. I say just make u equal to x plus x squared and dv equal to e to the negative x dx and roll with it. It will take a couple of rounds, but you don't have everything all separated. The result of the integration by parts gives us the equation x plus 1 e to the negative xy is equal to negative x plus x squared times e to the negative x minus the quantity of 1 plus 2x times e to the negative x minus 2e to the negative x plus c. Kind of ran out of room there. Now we're going to isolate y by dividing both sides. Well, we'll multiply. We'll multiply both sides by e to the x over x plus 1. The result's going to be y is equal to negative x minus 1 plus 2x over 1 plus x minus 2 over 1 plus x plus c e to the x over 1 plus x. Notice that among our fractions that have common denominators, we have a -1 and a -2. We're going to go ahead and combine those. Y equals negative x minus 2x plus 3 over 1 plus x plus c e to the x over 1 plus x. And yes, you could combine those last two terms if you wanted. You could get everything to have a common denominator, but I'm not going to bother with that. As far as an interval of solution, as we discussed above, I'm going to identify the interval x greater than -1. You could, if you wanted to, just say it was x is less than -1, but I'll go with the interval from -1 to infinity. Unless we have other information, it's arbitrary. And in this case, there aren't any terms that would go to 0 as x goes to infinity, so there are no transient terms.